Exam 3 will be next time during the regular class period. I said we put that on chapters 5 and 6, but I was only able to get through 6.2 last time. I didn't want to rush 6.3, so it's just chapter 5, 6.1, and 6.2. That's reflected on the practice problem set that I put up there. If you downloaded this immediately when I put it up late last week, there was a couple of typos in there, and I didn't have the answers on it over the weekend. I think Saturday night, I put up a new set that's got a couple of corrections, and then it's got all the answers to it. So you should have all the answers available if you download it. That's after Saturday night. Bring a calculator next time, and we'll go over some of these problems here at the end of class. I do want to make sure I finish section 6.3 because I should have had that done before now. So we'll do that today, and we'll do a little bit of review. Think if there's any practice problems you want to look at. I do have my usual office hour today. If you want to come by later, 12:30 to 1:20, just at the room at the end of the hall on the right there. Math and Computer Science, this building, end of the hall, room 113. Right. If during the day is bad for you, I know for some of you it is. Let's say there's one. Another one I'll be in again tomorrow, 4:30. To 5:40 or so. Right next door here in MCS 103. By then. Today I want to talk about parabolas. These are really, really important in all sorts of mathematics. They just come up all the time. I don't know if you've seen all the applications of these things. They're just amazingly frequent. If you have, for instance, an orbit around the sun, you can have a planet that can go on a circular orbit, or it can go on a slightly more elongated orbit. What is this more elongated orbit called? Everybody heard of that before? Yeah, it's an ellipse. And the sun is actually one focus of the ellipse. If you give it just a little more velocity, so it just has escape velocity, like an object comes from infinity, goes around the Earth and shoots back out. What shape is this? Where it just has it's a parabola. That's what we're going to do today. So just having escape velocity gives you a parabola. And for your information, it has more than escape velocity. It does a shape like that. Those are asymptotes out here called a hyperbola. Those are for other courses or maybe a little bit later in this course, a little bit. But you see the parabola comes up in there. If I take a ball, I should have thought to bring my ball this morning. Bounce it across the floor. Bounce, 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 bounce. What shape is the bounce? Actually, a parabola. If you ignore air friction and you assume gravity is constant straight down, it's not quite perfect, right? There's a little less gravity up here than what's down here, but it's negligible. For constant gravity, which it almost is at the surface, near the surface of the Earth, and ignoring air friction, it goes a perfect parabola. It also neglects the Earth is turning. It doesn't turn very far when the parabola doesn't out. So each bounce is a parabola. Very approximately. There's lots of other cases where it comes in. You ever seen a flashlight? An ideal flashlight, if you put the bulb right here, and the idea of a flashlight is it's supposed to take the light rays coming off the bulb, and if this is the mirrored surface, it's actually right around the surface of revolution. And you want it to shoot out in a straight beam, right? Using angle of incidence, this angle here, alpha equals angle of reflection, alpha, for all these beams. So if you take a tangent to here, this angle here is equal to this angle here on the other side. To make a perfect beam, what shape do you need for the dish here? You need a parabola, it turns out. A parabolic dish does that. Or if you have your satellite receiver, right? Satellite dish, what shape is this ideally to take almost parallel rays coming from a faraway satellite or another solar system or something and focus them to a point? The reverse of the flashlight, instead of focusing it into a beam, it starts from the point and makes it and collects them from a beam and collects them to a point. So solar collectors and radio antennas and all these kinds of things, telescopes, many telescopes, not all of them, it depends on the design, use parabolas because of this very important optical property that takes parallel light rays and focuses them to a point, including radio waves. Visible light and radio waves are both called electromagnetic radiation. They're the same thing, frequencies. You can't see radio waves. They're too low a frequency where you can see visible light. But it's all electromagnetic radiation, and there's other things like X-rays are also electromagnetic radiation. They have these same kind of behaviors. You want to be able to focus them in various instruments. So these things come up in these and actually lots of other places because of the important properties they have. What is a parabola? The graph, this is just to motivate it here, all those things, of a quadratic function is called a parabola. So the function is f of x equals ax squared plus bx plus c, and you want a not zero, where it's just a linear function, right? Is a parabola. This is what it's called. And so these are very important functions, right? They come up in all sorts of applications in engineering and physics and lots of other things. Now, how can we sketch a parabola, for instance? The most basic parabola, we can put a equal 1 and b equals 0 and c equals 0. Let's do a simple test case. F of x equals x squared has what graph? Really easy baby graph, right? You just make a little table here. Here's x versus y equals x squared, and you put 0 and you get 0. You put 1 and you get 1. You put 2 and you get 4. Minus 1 and plus 1. Right? Minus 1 squared is 1. And minus 2 squared is 4. 3 gives 9, and so forth. And so you get something that looks like this. The Romans used this shape quite a bit in their architecture, by the way. You go back to ancient Roman architecture, they have lots of parabolas in it. But you have these points. Here's 1, 1. Here's 2, 2, 4. Minus 1, 1. Minus 2, 4. It's kind of important to remember these basic points on the curve. Y equals x squared, the most basic parabola that we study. And then we say, how can we sketch other parabolas? Right? Well, we remember those graphing techniques, right? We can stretch and shift this by replacing what? X by x minus a and y by y minus b. And then by replacing x by x over a and y by y over b and move it around. In other words, I can write y equals a times x minus h squared plus k. That looks very similar to y equals x squared, but I've or y equals x squared, same thing. We're just saying here's the rule and here's the graph. But so this looks like y equals x squared, except it's multiplied by a. What does this do? If I forget the h and the k, suppose I just put y equals ax squared. Forget the h and the k for a second. What does that do?
Stretch it by a factor of a.
Yeah, it makes every y coordinate a times as big. So it stretches it by a factor of absolute value of a. It's absolute value of a times as tall. So if a is 2, it's twice as tall. If it's a is 4, it's 4 times as tall. And what if a is negative? Yeah, flips it upside down, makes all the way coordinates negative what they were, right? Flips it upside down. If a is negative, right? Now we want the h and k after that. Now from this equation, once I've stretched it, maybe flipped it, how can I move it around? Comma here. So y minus k equals a times x minus h squared does what? If I, in any equation in x and y whatsoever, I replace y by y minus a number and x by x minus number, what does that do to the graph?
Moves it right.
Yeah, does anybody else know that? Very good, you're right. Yeah, replacing in any graph, x by x minus h moves it h units in the x direction. Replacing y by y minus k moves it k units in the y direction. Think about this, right? I have y equals x squared. Let me put a simple example here, and I'll come back to that. Leave some space. Example. Y equals x squared. We know what that looks like. That's the baby parabola, right? Goes through 1, 1, minus 1, 1. I'll just draw 3 of these. 0, 0. Right? Now, what does y equals x minus 1 squared look like? Think about it. In order to have a point on this graph, I have to make, in order to square the same number here and get the same y value, I have to make x 1 unit bigger, right? So here, when x is 0, I square 0. Here, I have to make x equal 1 to square 0. Because I put in x equals 1, I square 1. I have to put in x equals 2 to square 1 here, right? 2 minus 1 is 1 squared. Well, I have to make x 1 unit bigger to get the same y value here as I did here. It just moves it over 1 to the right, right? So at every point is moved over, and this is 1, 0, and this is 2, 1, and this one is 0, 1. I just have to add 1 to every x coordinate on this one to get the x coordinate on this one, right? And otherwise, it's exactly the same shape because I square the same number just by making x1 greater. So this is, and that's what but you can do that in any graph whatsoever. It doesn't have to be a parabola. If you replace it in any equation, x by x minus h, it just moves it h units in the x direction, just like this moved it 1 unit in the x direction. Similarly, if I put, instead of doing that one, I'll say recall because we actually did this before. Y equals x squared plus 2. What does that do? Or like, let's do it this way. Y minus, let's do it this way. Let's just put this one plus k. I'm just going to do this as 1 step instead of 2. So if I put y equals x squared plus 2, how does that compare with this graph? Oh, come on, this graph, y equals x squared, it adds 2 more to every y coordinate, right? So every y coordinate is 2 greater, and I get this one. Instead of 0, 0, I get 0, 2. And so this one was moved over 1 to the right. This one moves up 2. And this one becomes, and so it's the same shape actually, because I just took the same points, same coordinates, and added 2 to every one of them. So this is 1, 3, and this is minus 1, 3. Every y coordinate shifted up 2, and that's what this does. Now, if I put those things together and put y equals x minus 1 squared plus 2. Now I did a shift of 1 in x and then added 2 to every y coordinate. Now I moved it over 1 and then to get this one, and then added 2 to every y coordinate after that. So this point down here that was at the origin moves over 1 and up 2. It's right here. But it's the same shape as the baby parabola. This is y equals x minus 1 squared plus 2. It just moved it over 1 and up 2. And the point is, if you've already stretched the thing and then you put x minus h and add, instead of x, and you add k at the end, this one moves the stretched graph, the stretched and or flipped graph, h units in x can be left if h is negative, and k in y, because you just added k to every y coordinate, and you replaced x by x minus h, moving it over h units. Just like this example, replacing x by x minus 1 moves it over 1, replacing adding 2 at the end moves it up 2. You can do that to the stretched graph also, which means that this is a really important equation. Sometimes they call it the canonical equation for a parabola, a vertical parabola. once you see that equation, you can graph any parabola. All right? Because what happens is, you can see this point down here is very important, right? There's a symmetry across this line. You sometimes call it axis of symmetry that goes through that point. And moreover, it's the lowest point when you do the bouncing ball problem. This point right here with the parabola upside down is the highest point the ball gets to. That's very important. How high did it go, right? And so we call this point the vertex. It lies on this axis of symmetry at the bottom of the parabola here. And so for the baby parabola, it's at 0, 0. But where is it in the other parabolas? Since this one just does a stretch, it's just going to make it a times its tall and maybe flipped upside down. So here's y equals a x squared. It still has a vertex at 0, 0, right? Where it hits its bottom point there. And when you then move it over, the vertex is the shifted point, HK. So the vertex of 1, the point where the thing bottoms out or tops out, depending on whether it's right upside down or right side up, the vertex is now at HK. And you have a stretch factor A, and it flips upside down if A is less than 0. If you use those three concepts, you can now graph any parabola. We can use that to sketch any parabola we want whatsoever. How do we do it? By moving the vertex to HK, stretching it by absolute value of A, and turning upside down if A is negative. That's all we do. And chalk is on my one. Move the vertex. These are just our stretching and shifting techniques we did before. Apply to a parabola. Move the vertex to HK, the point where it bottoms out or tops out. 2, stretch the thing by a factor absolute value of A, and flip upside down if A is less than 0. That's the whole strategy of graphing parabolas. But you have to put it in the form 1. So let's say any parabola 1 is graphed by doing that. But how do we put it into the form 1? The fact is that any quadratic function can be put into the form 1 by completing the square. Starting to come fast, isn't it? Slow me down if you need to. Quadratic function. What's a quadratic function? Y equals ax squared plus bx plus c. Just a second degree polynomial. Can be put in the form 1 by completing the square. It's canonical to be standard. Canonical form or standard form 1 by completing the square. And so then any graph can be, any parabola can be sketched. That pulls it all together. I give you a function ax squared plus bx plus c with a not 0. I complete the square and put it in this form, and then I immediately sketch it by these 3 steps. That's it. And like I say, these are used an extreme amount. They're often the simple examples. If you take calculus, they'll do a lot of simple examples that are parabolas. You have to know this stuff very well. If you're not taking calculus, maybe you don't care. They're still used a lot in algebra. All right. So here's an example. Suppose I said sketch a graph of y equals x squared plus 2x. That's a quadratic function, right? 1 times x squared plus 2x plus 0. Right? A is 1, B is 2, C is 0. It's allowed to make anything but A equal to 0. What does that look like? It's a parabola because it's ax squared plus bx plus c, right? So you notice that it's ax squared plus bx plus c, so it's a parabola. Does it open upward or downward? Yeah, if A is positive, you're not going to flip it. So if A is greater than 0, is no flip. Put that one last. But what's the stretch factor? Absolute value of A is 1, so there's no stretch. It's just the same shape as the baby parabola. And then where's the vertex? Well, I have to complete the square. Y equals x squared plus 2x equal to, what you do to make a perfect square, remember? You pull the coefficient of x squared out, I'll put 1 here times x squared plus 2x just to show, in general, you have to pull out the coefficient of x squared. Coefficient is number multiplied. And then you say, you take 1/2 of this number, remember, and you square it. 1/2 of 2 squared is 1. 1 squared is 1. So I have to add 1 in here to make a square. X squared plus 2x plus 1. Now it's a square, but I've changed the function, so I'll subtract 1 off here to cancel it. That's the same function because these cancel, but this is a square. So I'll write that as 1 times x plus 1 squared plus 1. There it is. This is of the form 1. All right? If I think of this as x minus a minus 1. Y equals 1 times x minus a minus 1. What else do we write? Squared plus 1. Evidently, h is -1, k is 1, a is 1. And I, by equation 1, deduce that the vertex is at -1, 1. What's subtracted here and what's added here? Right, because the x minus h is plus k squared and plus k. So I've got the vertex, I've got the stretch factor, there's no stretch. And I've got the flipping case, no flip. So all I have to do is take the vertex over to -1 plus 1, right there. And draw the baby parabola at that point. It's the same shape, right? Which means if this is the vertex -1, 1, I just go over 1 and up 1, and this must be 0, 2, and this one must be -2, 2, because it's the same shape as the little parabola. If I have trouble figuring these, I can just plug in, right? If I plug in x equals 0, uh-oh. Well, this is a -1. So this is a minus. Sorry about that. Minus. And this is, and the vertex is -1, -1. Sorry about that. Sign error there. That's not here. Vertex is at -1, -1. Here, and I make it the same shape. Now we got it. And so you go over 1 and up 1, just like the baby parabola goes through 0, 0, and you go over 1 and up 1, -2, 0, and the vertex is -1, -1. There we go. And if you want, you just plug some points in. Plug in x equals 0, you get y equals 0. Sure enough, it's verified. Plug in x equals 1. So you can plot some more points just by plugging in. But the basic 3 points, 0, 0, minus 1, 1, and 1, 1, all went to these 3 points by shifting down and over, doing no flip and no stretch. So plot more points by plugging in if desired. Not bad to put a couple of them in like I did, make sure you didn't make a mistake too. There's how to plot any parabola, right? Now, one more thing that's really useful about parabolas is just like the other functions we did before, is to find the intercepts. Remember how to find an x-intercept? You find an x-intercept where it intersects the x-axis. How do you find that?
Set y to 0.
Now, on the x-axis is where the y coordinate is 0, right? These are all the points where y coordinate is 0, so you set y equals 0. Intercepts. To find the y-intercept, where it intersects the y-axis, remember that? At x equals 0. We can also do those, and we would have found these. Here's the two x-intercepts, and this one is coincidentally also a y-intercept. Find another one here. Here's one off the homework, a couple of them off the homework. Turn this online. I'm going to give you a simple parabola, y equals 4x squared minus 32. What's the vertex? What's the vertex? This one, the square is already completed, right? Think of this as 4 times x minus 0 squared plus negative 32. It's a times x minus h squared plus k. Minus h and plus k. And I say the vertex is at hk, it's at 0, negative 32. The stretch factor is 4. The absolute value of 4 is 4. Flip, there's none because 4 is greater than 0. So all I have to do to sketch this one is put the vertex at 0 minus 32. Stretch it by a factor of 4. On the baby parabola, if I go over 1, I go up 1. How about this parabola? Stretch by a factor of 4, then if I go over 1, I should go up 4. At minus 28. Baby parabola go over 1 and up 1. This one go over 1 and up 4 because of the stretch factor 4. It's 4 times the stall. So I'm going to get these points. 1 minus 28. You can also get it by plugging in. Plug in 1, you get, oh yeah, minus 28, right? Minus 1, minus 28. But you can figure out it's just from the stretch factor. And here it is. It's 4 times as steep, pretty steep parabola, and starting way down here. Right? Some of these I'll just say identify from the picture because they can't draw on the line. Sometimes I'll ask you where's the vertex and where are the intercepts. What are the x-intercepts? So there's the vertex. Is it 0 minus 32? Read it off, h and k, right? What are the x-intercepts? Sometimes there are none. Be aware, but let's try. You put y equals 0, you put 0 equals 4x squared minus 32. Right? Just put y equals 0 to get the x-intercepts. This gives you, by dividing by 4, 0 equals x squared minus 8. That's easier. Well, you can factor this and solve it, or in this case, maybe it's even easier to just write x squared equals 8. x equals plus or minus the square root of 8 is plus or minus 2 square root 2. So these are the x-intercepts. In many books, they'll just say the x-coordinate is the x-intercept. So this is an okay answer on the test. However, I think on n infinity, they actually want you to put the point. So I think on here, you're supposed to put plus or minus 2 square root, 2 square root 2, 0, minus 2 square root 2, 0. I think this is what they want on n infinity. Check, but some books, they'll just put the x coordinate and say that's the x-intercept. Sometimes they'll actually put the points, depending on the book. How about the y-intercept? There's only going to be at most one. There's only going to be one, actually, because it's a function. If there was more than one y-intercept, it would have two y, it would fail the vertical line test, right? You just get one y-intercept by setting x equals 0, right? Y equals 4 times 0 squared minus 32. Well, we already know it from plotting the vertex. It's minus 32. So some books will say that's the answer. That's fine on the test. Or if you want to put the point, you put x equals 0, y equals minus 32. There's the y-intercept. I think that n infinity wants. Okay. That's how you do those kinds of problems. So there's the graph down here. You can see the graph online. I forgot online to move the camera back here, didn't I? So there it is. Find the x-intercepts, do this. Set y equals 0. The y-intercept set x equals 0. All right. How about this one? Here's another y equals 3x squared plus 16x minus 12. This is number 8. Find the vertex and intercepts for this one. How do I find the vertex? Well, you can put it in that canonical form or standard form, divided by 8. My y equals 3/8x squared plus 2x minus 3/2. I divide by 8. Why am I dividing by 8? I want to put it in y equals ax squared plus bx plus c form, right? I'm going to tell you an easier way to find the vertex. You can complete the square like we did before. It's certainly easy to do that, but when you've got 3/8 in there, it's kind of a mess. You can instead memorize this formula, which comes from completing the square, that the vertex is always at, by completing the square, general formula. At x equals minus b over 2a. I think it's worth memorizing this. The vertex always comes out there. If you do the stretch and complete the square, what comes out in completing the square is always this number. Lack of time, I think I won't derive that, but when you complete the square, that's what you get. I'll call that equation 2. Did I not? 3. All right. So in this case, once I put in y equals ax squared plus bx plus c, rather than complete the square, I'll do it faster. I'll just say it's minus b over 2a. So h, the x-intercept, trying to complete the square. I put x or h, it's the same thing. H is minus b over 2a is minus 2 over twice 3/8. Well, let's see, the 2's cancel. So it's minus 8/3. Doing a little bit of canceling and reciprocals there. And then what's K? You just put in what X is, right? K is equal to the Y coordinate is 3/8 times minus 8/3 squared plus 2 times minus 8/3 minus 3/2. You just put into the equation, into the quadratic function, 3/8 x squared plus 2x minus 3/2. Get K. And so let's see, it's 3/8 times minus 8/3 times minus 8/3. Well, these minuses cancel. This is minus 8/3 squared. And let's see, the 3/8 cancels the 8/3, that must be 8/3. Minus 16/3 here, top times top, think of this as 2 over 1, top times top over bottom, 16/3. Minus 3/2. Bunch of fractions, huh? But this is what you have to be able to do, right? We've got 8/3 minus 16/3 minus 3/2. Oh, boy, I still have a bunch of fractions, even though I didn't complete the square. How am I gonna get that? Okay, you're very, very good at fractions when you come out of, you need them afterwards, but you need them for this class too. Remember how I add and subtract fractions? And this should have been a plus, right? Plus, oh no, because it's minus there, right? Okay, so that's right. I put them over a common denominator, right? The least common multiple of 3 and 2. What is the smallest number that 3 and 2, the two denominators I see here going? 6, yeah. So I'll multiply this one top and bottom and get 16/6. This one top and bottom by 2 to get 32/6. And this one top and bottom by 3 to get 9/6. Now they're all over 6. This one top and bottom by 3 to make 6. This one, these two top and bottom by 2 to get 6. 16 minus 32 is minus 32. Minus 9 more is minus 41. All over 6. There's the Y coordinate. So that's K and that's H. The vertex, good thing we memorized the formula. It's the point, minus 8/3 minus 41/6. Now I'm sure I didn't make a mistake after all. It has the minus 8/3 minus 100/3. Got something wrong here. What did I do? Maybe that's divided by this by 8. Vertex, right? And I put in minus 8/3, which is right. Well, I know what it did. That's all right. 16 minus 32 is minus 16. Minus 9 is minus 25/6. 16 minus 9 is minus 25. That's still not what they're putting in the answer sheet. Well, that's what you do. You put h equals minus b over 2a, calculate the vertex, then you just plug it in, or the x coordinate of the vertex h. You plug it in to get k. Apparently, I can't do my fractions. Anybody see a mistake in there? Looks like I did it right. B over 2a. We can plug in any. Oh, I see what they've got a mistake in here. Oh, I just got on the, let's see, hold on. I see what's going on. I had an 8 here and they don't. I just did a different problem. How did I get a different problem? All right. So apparently what I did is right. What they did is right. I just had an 8 here that they didn't. So for what we did here, that's right. This is when you do the problem, there will be an 8 here and you'll get the same x coordinate, but a different k. So this is actually okay. It just doesn't match the answer on there because I did a different problem. Any questions on that one? Put it in the form y equals ax squared plus bx plus c. Compute x equals minus b over 2a to get the x coordinate. Plug it in to get the y coordinate. Now, where are the intercepts? I want the x and y intercept, right? All I have to do is put x equals 0 to get the y intercept, right? And y equals 0 to get the x intercept. So the x intercepts, I put y equals 0. I can put it equals 0 here, and that's nice, and that works. But why do I want to use fractions when I don't have to? Let's put it up here where there aren't any fractions. Put it in the easy equation. For the x-intercepts, I'll put y equals 0 and get 8 times 0 is 0 on the left equals 3x squared plus 16x minus 12, right? So there's the x-intercepts by the easier equation. This one before I divide. What are the x-intercepts? How do I compute it? You guys know how to do this one. How do I compute the solutions to this? X-intercepts are always the solution to the quadratic equation, right? This is ax squared plus bx plus c equals 0. I get by the quadratic formula, always it works for finding the intercepts. X equals minus b is minus 16 plus or minus square root b squared minus 4 times a times c is minus 12 all over 2a. There it is. The x-intercepts are these points. I just have to figure them out. Minus 16 plus or minus. So this is 256 minus plus 144. It's 400. So this is square root of 400 is 20. Make some real fast numbers in there. All over 6. So it's two solutions. Minus 36 over 6. I subtract. Plus 4 over 6. If I add, it's minus 6 and plus 2/3. Those are the x coordinates of the x-intercepts. If you want the points, and this will be fine for the test because this is the answer in the books. Minus 6 and 2. But you actually have to put it in here to get the y coordinates. So when you put x equals minus 6, now y equals, let's see, 3/8 times minus 6 squared plus 2 times minus 6 minus 3/2. I have to do all these fractions. 36. Oh boy. Anyway, let's put equals dot, dot, dot. gives the intercept. And then x equals, bring a little because I want to do some review now. X equals 2/3 put in here, we get y equals 3/8 times 2/3 squared plus 2 times 2/3 minus 3/2 equals dot, dot, dot. This gives you the x-intercepts for this equation. So what happens is you can always find the x-intercepts by solving a quadratic equation and then putting those in to get the y. This will give you the x-y coordinate of the two vertices, the two x-intercepts. Now finally, the y-intercept, how do I get that? I said x equals 0. So I put in either of these, in this equation here, y equals 3/8 x squared, 0 squared, plus 2 times 0 minus 3/2. Oh, and it's equal to minus 3/2. Oh, what am I saying over here? This is the x-intercept. I'll get 0. All right, so it's minus 6, 0. The x-intercepts are minus 6, 0, 2/3, 0. Those are the x-intercepts. And over here, what we get is 0, 3/2. X equals 0 and y equals minus 3/2. So our function, which is slightly different than the books on this problem, there's the y-intercept, here are the x-intercepts, and then we found the vertex already. Okay, that's it pretty much on that section. I want to take what time we have left and do some review problems. Try those things out of 6.3. That'll be due after the test. Trying to see if there's anything else we desperately need to do. I guess there is. There's one last thing I need to mention, I guess. This doesn't have to do so much with parabolas, but note. You notice that when you go to solve for the x-intercepts, you always get a quadratic equation, right? You put y equals ax squared plus bx plus c. To find the x-intercepts, you put y equals 0, and you got a quadratic equation. To solve a quadratic equation, ax squared plus bx plus c equals 0 for the x-intercepts, we get an interesting result. If a, b, and c are rational. What does rational mean? Who knows what rational means? We've mentioned this before too, but if you don't use it, it goes away quick. What are rational numbers? We haven't used it. Really, rational numbers are numbers that can be written as ratios. They're fractions. So if they're rational, that is, they can be written as fractions. An integer divided by an integer, right? Like, is this a rational number? It's not, because of the square root 2. But this is a rational number. If I take an integer divided by an integer, that's a rational number, a fraction. This is not, this is. You have to take a ratio of 2 integers, that's a rational number, a ratio, a fraction. If those are rational, then the solutions, call that 4, of the quadratic equation 4, consequently the x-intercepts, that are not rational numbers, call them irrational, not expressible as fractions, come in conjugate pairs. What are those? The solutions here come out to be C. I can't use A, B, or C. I'll put hats on them. A hat plus B hat square root C hat. A hat minus B hat square root C hat. So if you can't write them as fractions, then they always come in pairs like this with a plus square root here and a minus a square root here. Then also, if A, B, and C are real numbers, what are real numbers? Those are numbers that any numbers can be written as decimal. Isn't that all numbers? It's all real numbers. What we want is no I in there, no square root minus 1 in there. Those are complex numbers if they have square root minus 1 in there. If they're real, not including I, then any solutions of 4 come in complex conjugate pairs. A hat plus B hat I, where I is the square root of negative 1, and A hat minus B hat I, where I is the square root of negative 1. And again, I use these hats on here to say these are different numbers than the A, B, and C in the original equation. I just didn't want to use U, V, W or some strange letters, so I picked A, B, C still. Those are the two theorems, and they all can be proved with the quadratic formula. I just want to show you a simple example so you can see. This will be actually a practice for your test. This is the end of the material for parabolas. But suppose I wanted to solve, this is review now for the test. All that stuff will not be on the test. Okay? So this might. Suppose I said solve x squared plus x plus 2 equals 0. Suppose I'm finding the x-intercepts of y equals x squared plus x plus 2. What would they be by solving this equation? This for your next test, I'm going to ask you to do the quadratic formula, and I might ask you one of these where you get these kind of answers. Remember, the quadratic formula always works. Minus b, I look at the numbers. A is 1, b is 1, and c is 2. Right? So minus b plus or minus, you have to have this memorized. Square root b squared minus 4ac, because I'm going to ask for a quadratic formula here over 2a. So it's minus 1 plus or minus square root 1 squared minus 4 times 1 times 2, all over 2 times 1. And the solutions are minus 1 plus or minus square root of minus 7 over 2. Those are the solutions. Right? Right now, this is minus a half plus square root of 7 is square root of negative 7 can be written as square root of 7i over 2. And minus a half minus square root of 7 over 2i. Look, it's an a hat plus b hat I, a number plus a number times I, and the same a hat minus the same b hat times I that came in a complex conjugate pair. So these are irrational conjugate pairs. Those are complex conjugate pairs because they have complex numbers. There's a lot of stuff in it. But this is a problem I might ask you for the test next time, because one of the things we did, we said we can solve this even when you get solutions with I in it, right? Square root of -1. These are the two numbers you can plug in there that would solve that equation. Yes, they're imaginary numbers, but they lead to real solutions for engineering. But they came in conjugate pairs. Whenever you have numbers without I here, A, B, and C, if there's any numbers with I in here, they'll come in pairs where one's plus and one's minus the same number times I, and the same number without I. So that's that example. Oh, I need to. Here's another example. We should do the one off the problem set here. Again, I'm doing review problems here. Suppose I gave you x squared plus 2x plus 5 equals 0 to solve on the test. Wait a minute. 3x squared minus 2x minus, no, this one. 3x squared minus 2x equals 5. Suppose I said solve this. Let's solve that. This is your test problem next time.
Move the 5 over first.
Yeah, whenever you solve one of these, you have to get 0 on the one side. Otherwise, the formula doesn't apply and you can't factor it. So if you're factoring, you have to get it over to factor. If you're using quadratic formula, you have to get it over to use the quadratic formula. Always get 0 on one side. All right. And once it's in that form, I can either try factoring. Sometimes it works and sometimes it's too hard to guess the blanks. Or I can just go straight to the quadratic formula. It always works. So I'll put minus b minus a -2 plus or minus, just using this formula. Square root b squared is 4 times a times c. All over to a. There's a solution just like that. You just write it down from the formula. See why it's such an important formula? These things come up all the time, you know, solving the bouncing ball problem or anything like that. So let's see, we've got 2 plus or minus. This is 4. Let's see, 20, 60, 64, plus or minus square root of 64, all over 6. All right, oh, square root of 64 is 8, so it's 2 plus or minus 8 over 6. Well, I can get 14 over 6, which is 7/3. What am I saying? 10 over 6, which is 5/3. Or I can get minus 6 over 6, which is -1. Those didn't come in conjugate pairs. Why not? The answer is they don't have to. There's no square roots left and there's no i's left. This is okay. Ones that don't have square roots or i's in them don't have to come in conjugate pairs, and these didn't. Right? Let's try this one. X squared plus x minus 1 equals 0. Suppose I solve this one. So if they've got i's in them, then they have to come in conjugate pairs, a plus bi and a minus bi. How about this one? Again, now a is 1 and b is 1 and c is -1. So I put x equals minus b, b, c, plus or minus square root b squared would be 1 squared minus 4 times a times c, all over 2a. Gives me -1 plus or minus square root of 1 plus 4 is 5, all over 2. What have I got? If you break it up into two pieces, this is -1 over 2 plus or minus square root 5 over 2, also known as -1/2 plus or minus 1/2 square root 5. It is an a hat plus or minus b hat square root c hat. Came in conjugate pairs. So when you have a square root that won't go away, it'll come in a pair, a plus b square root c and a minus b square root c. If the square roots go away, you get it. And if the i's don't go away, you get one with a plus I term and one with a minus I term. So that's your last, that's item number 22 here. This is 22. C. This one is 22p. I want to make sure you can do this because I'm going to ask you some questions like that. Find the conjugate pairs here. Find the solutions here. Find the conjugate pairs here. You want to be able to do all those things. You want to be able to factor also. But those will come into play in the parabolas too, as you saw. Okay. Anything else you want to see off the practice test? Have you been trying some of those, or I'll probably make a lot of the problems similar to these practice problems. So make sure you can do these all. Come by and see me. Also, the tutors are at the end of the hall. MCS 100. It's the computing terminal room. You can go in there. Somebody had a badge on that says tutor, and they'll help you with anything. They tutor through calculus. So you can just sit there and work on your homework if you want. If you can't find me or whatever, they'll do the best they can. Did all the other problems, are they all doable? Anything else? Look at 19A here. I want you to be able to factor. I'm going to ask you a factoring problem, right? This factoring is extremely important in algebra. Solve by factoring. X times 9x plus 32 minus x or equals x plus 8 squared. How in the world do I solve that? I solve that? Your test next time. What do you do? You recognize that if you multiply it out and write it as this times this is 9x squared plus this times this 32x equals, well, how do we do this one? Is this x squared plus 64? It's not. What did I do wrong? Oh, no, that's somebody does this. This is on your ACT all the time. They try and trick you. You have to FOIL, right? It's not this squared plus this squared. It's x plus 8 times x plus 8. So it's x squared plus 8x plus 8x is 16x plus 8 times 8 is 64, right? So FOIL, don't just square this and square this. That's somebody always does that on this test. So don't be one of those people, right? Come to class and FOIL, right? All right, so now I multiplied it out. Now what can I do? I can group like terms, subtract all these over. Subtract x squared on each side to get 8x squared over here. And no x squared here, right? So I'll subtract x squared on each side. And I'll subtract 16x on each side. So then I'm left with 16x here. And I'll subtract 64 on each side. And this equation is equivalent to this one by multiplying out, is equivalent to this one by subtraction. And now what kind of equation do I have?
Quadratic.
There you go, quadratic equation. Ax squared plus bx plus c. We can always solve these, right? Every time the quadratic formula works, or factoring often works. Boy, there's a lot of choices for factoring. Right, I'm going to leave a little space here. Blank x plus blank times blank x plus blank is how I factor this. There's a lot of choices how to multiply to 8. 8 and 1, 4 and 2, 2 and 4. Over here, 64 could be 8 times 8 or 16 times 4 or 64 times 1. How do I reduce my number of ways to pick for the blanks?
Take half of 64.
There we go. I was waiting for somebody else. You're too smart. You know, yeah, divide by 8. Thank you. Divide by 8. All these are divisible by 8. I'll write this equivalently as x squared plus 2x minus 8 equals 0. That really reduces my choices for the blanks. Divide through so I get the smallest integers possible here. Remember, integers are numbers with nothing after the decimal point. Now it's reduced. To get 1x squared, I just have to put 1 here and 1 here. There's only one choice, right? How much easier is that? Now, 8, there is a minus 8, there is a choice. I can put 1 and 8, 1 and minus 8, or minus 1 and plus 8, or I can put 4 minus 2, or minus 2 and 4. But that's about it, right? I can't multiply 8 with integers any other way. And if it's not integers, I won't be able to guess what goes in the back. I'll have to use the quadratic formula. So I told you factoring, there's going to be integers that fit in here. We just have to guess what they are. All right, quadratic formula, I'll always tell you what goes in here. But this time we're going to be able to guess them because I said factor. Well, if I put 8 and 1, I'm never going to get a 2x in the middle. What if I put a minus 4 and a 2? What's going to happen? I'll get minus 8 here, but I'll get a negative in the middle. X squared plus 2x minus 4x will be minus 2x. That'll be negative. If I put plus 4 and minus 2, that'll do it, right? Now I FOIL out the check. X squared minus 2x plus 4x is 2x minus 8. I've got it. It factors, right? Just FOIL to check it. Right? First, outside, inside, last is FOIL, all possible pairs. So written a little neater here. This is x plus 4 times x minus 2 equals 0. So what are the solutions? Yeah, x equals negative 4 or plus 2. X equals negative 4 makes the zero product property says either this is 0 or this is 0. To make this one 0, you need x equals minus 4. To make this one 0, you need x equals 2. There's the two answers. Easy. First factoring. I'm going to ask you factoring. I'm going to ask you a quadratic formula on this test. Those are very important. Not the others. Did you look at all the others? Anything else, Steve? Going through them, I'm going to see anything you want to look at. How about this one? 12. Chuck, my nails are about to wake you up here. All right. 12 says express the exponential function p of t equals 30 e to the 0.1 t in the form a number p0 times b to the t. It's a single number to the t instead of e to the 0.1 t. How do I do that? Oh, I think that's because it's kind of tricky, but it's not so hard. Then I'll say, is it increasing or decreasing? Yeah, what you do is you rewrite this as 30 e to the 0.1 all to the t by your property of exponents, right? A to the b to the c is a to the b times c. So 0.1 times t here can be written as an exponent of exponent. And so this could be b, right? And this would be p0. Look how easy that is. And t. So evidently p0 equals 30. B equals e to the 0.1. I just have to run that on my calculator. You can do exponentials on your e to the 0.1 comes out to be 1.105 approximately. So these are the answers I'm looking for in the blanks. When you rewrite it this way, we say this is actually 30 times 1.105 blah 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 to the t. P0 b to the t. And that's what you put in these two blanks, and then t equals t. It just goes in. Have you had any troubles on any of the others looking at them last several days? Here's what I want you to be able to do for sure. I want you to be able to solve equations with logarithms and with x up on the exponent. Have to be able to do both those kinds. So as I said, solve for x. This is 7c. solve for x. I say log x plus log of x minus 99 equals 2. If x is in a logarithm, how in the world am I going to solve it? Please. That's the fun. Use the properties to combine logarithms, right? Logarithm of, if you like, m plus logarithm n is logarithm of n times n, right? Some logarithm is the logarithm of the product. So you take x times x minus 99. Log of x times x minus 99 is equal to 2. I just combine the logarithms that log m plus log n is equal to log of n times n. Now, once I've got that, it's equivalently, just combining these two. The left side is this, the right side is still 2. Now, how do I solve this one? Okay, so I can distribute the x log of x squared minus 99x equals 2. And now what do I do?
White flash on the screen.
And I'll take 10 to each side because the 10 to the log base 10 undo each other. So I'll take 10 to the left equals 10 to the right. Now 10 and log base 10 undo each other. I just got x squared minus 99x equals 10 squared, 100. Ah, there it is. X squared minus 99x minus 100 equals 0. I'll put 0 on the right hand side. And now I can solve it by factors. So by factoring. Let's see. X minus 100 times x plus 1 apparently does it, right? X squared plus x minus 100x is minus 99. Minus 100, sure enough, there it is factored by checking my FOIL. So x equals 100 to make this factor 0, or x equals minus 1 to make this factor 0. Those are the solutions, all right? Yeah, I got one thing. I'm going to do the last thing here. I want you to be able to solve these if x is in an exponent. Solve for t. This is 14. All right. Good chance I'll ask all these kinds of problems on here. This is the last one for today. We've got time. Solve for t. Y equals 100. K times 1 minus e to the minus t. How do I solve for t when t is in an exponent? Remember that? When t is an exponent, you isolate the exponential and take the logarithm, right? So we're going to isolate that's exponential that contains t. Take the logarithm of each side to bring the exponent down. You can use either logarithm base e or logarithm base 10. Let's take natural logarithm. It doesn't matter which one, actually. So I'll take and divide by k and get y over k equals 1 minus e to the minus t. I'm just trying to get the e to the minus t by itself. I'll subtract 1 and get y over k minus 1 equals minus e to the minus t. It's not quite isolated. I got this nasty minus. So I take minus each side and get 1 minus y over k equals e to the minus t, right? Now it's isolated, exponential all by itself, so I take the logarithm. I'll take natural log. ln of 1 minus y over k equals ln of e to the minus t. I can take the common logarithm too, and it works. But this is even better. Log base e of e to the minus t. What is this left side? Yeah. Log base e undoes the exponential base t. I just get my negative t. Right? Just like log base 10 of 10 to the t gives you t, log base e of e to the t and minus t gives you minus t. So I've got minus t is ln 1 minus y over k. Consequently, so I multiply by minus 1, t is minus the natural logarithm of 1 minus. See, you always do that, and it's very important in all the sciences to do with it. Time to get out of here. Bring me a class of questions. See you next time.
Thank you.
Yeah, you're welcome. You too. Well, you guys are tall when you stand up.
Yeah.
Sports team right in against you.
It's like small.
Yeah.
Thank you.